Today's video is going to be a bit shorter since we're just going to introduce the classes of pericyclic reactions, and that's going to serve as an introduction leading up to more in-depth videos exploring how each class of pericyclic reaction functions. To begin with the overview, pericyclic reactions are reactions that occur in a concerted way, wherein all the bonds break and form simultaneously. This means there's essentially no reaction intermediates, there's just a singular transition state, starting with the reactants and ending with the products. This transition state is cyclic, wherein all the participating orbitals interact across all components of the reaction, from beginning to end. The reactivity of pericyclic reactions is influenced by the number of electrons that are involved in the transition, as well as the method whereby you apply energy to that reaction. And typically it's either thermal energy, so you heat up your reaction mixture, or it's photochemical, so you apply relatively high energy photons and that supplies the energy to break and form bonds. Overall, there are 5 classes of distinct pericyclic reactions. The first of these is electrocyclic ring closure or ring opening. So a lot of these reactions, we can talk about the reaction proceeding in either direction, be that forming or breaking of bonds. So in this example, we're talking about a ring closure reaction, and it's classed by a new bond forming, highlighted in red, and it derives from the terminal p orbitals found in the starting material. So these terminal carbon atoms here. The classification of these reactions comes down to the number of electrons involved in the transition. So we have a look at our starting product. We have 1, 2, 3 double bonds. Looking at our product, we can see that none of those double bonds exist in the product, meaning they're all involved going from this form over across into this form. We're not going to consider the sigma bond component of these double bonds, so each double bond contributes 2 electrons into the reaction. So this 6 electron classification comes from 2 electrons here, here, and here. All of those have undergone a transition to get to this final product here. Second example, we're looking at a diene. It's a 4 electron transition looking at these 2 double bonds shown here, and we're forming this new bond shown here in red. Next class of pericyclic reaction are cycloaddition or reversion reactions, and these are a union of 2 independent pi systems, which we classify in terms of this M plus N nomenclature. Any sigma bonds that arise, shown in red, occur at the expense of pi bonds found in the starting materials. So in our first example, it's a 2 plus 2 cycloaddition reaction, and I've highlighted the 2 sets of conjugated atoms that fuse to give our product. So in blue, we've got 2 carbons shown here, conjugated to give a double bond, and in pink, we've got a carbon and an oxygen conjugated to give a ketone. When we irradiate this to give rise to a photochemical reaction, what we see is we lose both of our conjugated systems and we form 2 sigma bonds shown in red. Second example is a thermal cycloaddition reaction. This time it's 4 plus 2. So we can see we have 1, 2, 3, 4 carbon atoms that are conjugated together, and it's going to fuse with a double bond. So 1, 2 carbons here. So that gives us our 4 plus 2 nomenclature, and we can see we're forming 2 sigma bonds at the expense of our 2 double bonds. Although here the leftover electrons form a new double bond situated in between where the diene was located. Third type of pericyclic reaction are chelotropic reactions. Here, 2 bonds are formed or broken at the location of a single atom. So quite similar to our previous example, but it has to be localized at a single atomic point. We use exactly the same nomenclature as before, although at our single atom point, we're just going to call it a +1 reaction. So I suppose arguably there are 0 conjugated atoms if there is only 1, but we're not going to say 0, we're going to say 1 because it's localized at a single atom position. So here we can see our 2 conjugated atoms. It's going to react at this single carbon location. We are forming 2 new sigma bonds at the expense of our initial double bond over here. Got another example, so this time it's a 4 plus 1 chelotropic reaction. So we have 1, 2, 3, 4 conjugated carbons, and again, our reaction is localized on a single sulfur atom. We have our 2 new sigma bonds forming, shown in red, and that's at the expense of our 2 double bonds over here, although like before, the leftover electrons form a new double bond between the location of those initial double bonds. Fourth class are sigmatropic reactions. Here we have a migration of a sigma bond, again shown in red, and this occurs with a rearrangement of the pi bonds in the starting material. Slight difference is that the number of sigma and pi bonds at the beginning of the reaction is equal to what you find in the products. So the number of sigma and pi bonds are constant across the reaction. This time the nomenclature has 2 numbers followed by a dash shift. And these numbers relate to migration of this red sigma bond shown here. So the M value corresponds to how far the sigma bond migrates on the pink side, whereas the N value corresponds with how far the sigma bond migrates on the blue side. So looking at this example here, it's a 1-3 shift. A 1 on the pink side effectively means that it hasn't shifted at all. So if we look at our starting material and our product, our sigma bond has not moved away from this R group. It's still there. If instead we look at the N value, so the 3, we can see that our sigma bond has migrated from this 1 carbon atom all the way across to this 3 position carbon atom. So that's where the 1-3 shift comes from. The sigma bond hasn't moved from the R group, giving you the 1, but it has migrated from the 1 carbon up to the 3 carbon position. So it's a 1-3 shift for that reason. We can look at a slightly more complicated example. So this one is a 3-3 shift. Again, we're going to focus on this red sigma bond, looking at the starting material as well as the product. And we can see that the sigma bond has migrated firstly from the 1' position across to the 3' position. And it's also migrated from the 1 blue position across to the 3 blue position. So that gives us our 3-3 shift. Effectively, our bond has migrated from this position, broken both of these bonds, and shifted all the way across over to the 3 position here. And we see this movement of our double bonds across like so. Just at this point, we're going to touch upon some really common sigmatropic rearrangements that we'll talk about in future videos. So if this X atom is an oxygen, this reaction would be classed as a Claisen rearrangement, whereas if this would be a CH2 group, that would then be a Cope rearrangement. So both of those are relatively well-known chemical reactions, and we'll cover those in a future video. Final class, this is our group transfer reactions. And this is where one or more functional group gets transferred across to the second reactant. Now, all of the examples we're showing, we're basically migrating hydrogen atoms between our two groups, but this can be more complicated than that. It could be a methyl group or some other atom other than hydrogen. These were just the examples that I picked. So focusing on our red functional groups, we can see that they are migrating from this reagent across over to this side. And we also get a migration of our double bond from one reactant over to the other. Bottom is another example. It's effectively a transfer of hydrogen atoms again, and at the end we're producing nitrogen gas. So that's going to be an irreversible reaction, liberating nitrogen gas, which is going to drive that reaction all the way to completion, giving us this product. One relatively known named reaction would be the Ene reaction, of which I'm showing an example sourced from Wikipedia. So again, we're getting functional group transfer. We've got our hydrogen jumping across here, but we're also forming a brand new sigma bond that links all of these components together. So that's the very quick classification video of pericyclic reactions. In the next couple of videos, I'm going to delve more deeply into the how and why these reactions actually occur. It'll cover all 5 classes of pericyclic reaction as well as the theory that underpins them. There'll also be focus placed on these named reactions that come up more frequently in organic chemistry. I'll also invoke frontier molecular orbital theory to show you how these transition states look when you get this one-step cyclic transition from our reactants to give our products. So that's it, bit of a prelude to what's to come, but hopefully you found that interesting. Thanks for watching.